This brings us to the definition of a very important quantity, directivity. Directivity is the radiation intensity of your antenna divided by the average radiation intensity of your antenna. Or, as I've just said, that would be the same as dividing it by the radiation intensity of an isotropic source with the same radiated power. Now, a lot of the time, people will say, what is the directivity of an antenna? And they don't want you to give a function of theta and phi. They want to tell you the max directivity of that antenna. So we'll write directivity as a function of angle here, but we will also write d max is u max over u average. Kind of obvious, but kind of important. Now, both of these terms have the radiated power in them, which is an important thing. This directivity is a measure of the pointiness of a pattern. All the power has to go somewhere, and what we're measuring is just how tightly is that power being squeezed into one particular direction. That's why we call it directivity. Imagine it like a balloon full of air. You have a finite amount of air, but if you squish the balloon, you can make all of the air sort of go into one side of the balloon. That's what directivity is doing. Now the thing is that this is normalized to the average value of the radiation intensity. So we can't have the maximum value of directivity in all directions, because that would mean that U average and U max are equal, and then that's just an isotropic source. So you can't just increase your directivity in all directions at once. There's a finite amount of directivity, and it has to go in one. You have to increase your directivity by restricting the number of directions that the energy is going to, or that the power is going to. The other thing to note here is that the minimum possible value of directivity is where you do have an isotropic source and it is radiating equally in all directions, because then U max is equal to U average. So isotropic sources have minimum possible directivity, and that would be D equals 1, the D max equals 1. Obviously, if you're looking at the angle-dependent directivity, you could have a direction where the radiation intensity is 0. That would be called a null. But in general, it's not going to be 0 everywhere unless it's not radiating. So somewhere else you will have more radiation intensity, and it will not be 0 everywhere. And then your directivity will be greater than 1, because it wouldn't be equal in all directions. All right, so if we're talking about an antenna that's radiating, the radiated power density from that antenna is going to be equal to the radiated power over 4 pi times the directivity times e to the minus, oh, actually not, because that's not a power term. So if we're talking about the radiated power density from an antenna, that radiated power density is going to be the total radiated power over 4 pi times the directivity as a function of angle. So that angle is from the point of view of the antenna that is radiating. So if I have an antenna that's radiating and I'm over here looking at it, here's a cartoon picture of an eyeball, and I want to know what is the radiation power density at this point, I use this equation. Cool, that's an antenna in transmit mode. What about antennas in receive mode? What if I have the same situation, but instead from my eyeball, I have some incident power, and I want to know how much does the antenna receive. Interestingly enough, that depends on directivity too. The power available from a receiving antenna is the incident power density times the effective aperture, assuming that polarization is perfectly matched, because we haven't talked about polarization yet, so we're kind of going to ignore the concept of polarization mismatch. What is effective aperture? Effective aperture is the wavelength squared over 4 pi times the directivity as a function of theta and phi, now from the receive antenna's point of view, which means that effective aperture is also a function of angle. For small antennas, effective aperture can actually be considerably larger than their physical size. But for large antennas, the effective aperture can be about the same size as the physical size and usually a bit smaller. So now we've talked a lot about how do we talk about radiation patterns and how exactly is the power that's radiated from an antenna distributed over space. Hopefully that gives you some tools to start working on Project 1.